Okay, so we have already taken a long time talking about matter and how matter changes the state of matter and so on. We dealt with liquid when we did solutions. We deal with solids most of the class. So now we are going to take a look at gases because they are quite important in a lot of the chemistry calculations and activities that do happen in nature. So we'll go over the characteristics of gases, then we'll jump into the different type of gas laws that describe gas behaviors. In lab, you explore the behavior of one of those gas laws, which was Boyle's law, which we'll go again through today. And we'll go through all of them. You have an activity and homework on partial gas laws. That's your only homework on gases. I'm going to let that be the review for that part. I'm going over partial pressures here today because you'll have to investigate that already in order to do that homework. So that's enough for what you need to know. Okay, so we'll start with the characteristics of a gas. So a gas, if I were to draw it in a container, particles are very spread out because they're in constant motion. So they're spread out. They're always colliding with the container. They have kinetic energy because they're moving. They have low density. Let's see what else. They're moving, they're spread out, colliding. They have kinetic energy. Each particle behaves by themselves. They don't interact with each other. And that's quite important, especially when you're doing the partial pressures Dalton law. So if I have a particle of a gas, that particle is going to be moving, it's going to hit the wall, bounce back. It doesn't lose energy, it's in constant motion. If it sees another particle of a gas, it's just going to ignore it. That's why you can calculate the pressure for each of the gases inside a container because they behave by themselves when they contribute to the total pressure of that container. Now, when we describe gases, we sometimes use the term the gas is at a STP condition or standard temperature and pressure conditions. You need to know these ones. They're not given to you in the reference tables. You have to remember them. STP conditions are when the temperature is 273.15 Kelvin or 0 degrees Celsius, 1 atmosphere, and when the temperature and the pressure are those conditions, the volume is 22.4 liters. It simplifies a lot of work. Remember when we were doing the moles calculations, we said that the volume was 22.4. That's because we were assuming STP conditions. And it only works when it is at STP conditions. You will not see it in this class, but in Chem 1, we are going to prove that. And you have a lab where you are going to calculate this value experimentally. So there's more layers to this, but for now, knowing that STP conditions are these three conditions, You are golden. You'll be able to do any problem that I throw at you. Okay, so gases are described by four different variables. Pressure, which is the force of the gas particles colliding with the walls of the container. Volume is the space that it occupies. Temperature is the kinetic energy of the gas particles. And then moles, which is the quantity of the particles of the gas. So you have four variables. Those four variables are going to combine each other in different ways and give birth to the different gas laws. In all honesty, I can only give you one gas law, and that's the ideal gas law. And from the ideal gas law, you can derive any of the other equations. So you don't really have to memorize all 4 or 5 equations. As long as you know one, you can derive the others, and I'll try to show you how that is done as we go through each gas law. And once you see the pattern, you'll be able to do it easily. Okay, so before we can do that, let's do a couple of things because we are going to need them when we do the gas laws, and that is that pressure. Pressure is measured in different units. Unfortunately, scientists couldn't agree on just one. We have several, and you have to kind of know them. There's no other one around it. So the basic one is the 1 atm because it's a STP condition. So 1 atm is the same as 760 millimeters mercury. It's the same as 760 torrs. It's the same as 101.3 kilopascals. It's the same as 14.7 psi. So any one of those measurements, they all equal 1 atmosphere. And I can use that to convert between units. So we are going to do something similar that we did at the beginning of the semester, which is unit conversions. I have an example down here. It says I want to convert 745 millimeters mercury into psi. So I always start with the unit I am given, which is 745 millimeters mercury. And then I know I have to cancel the millimeters mercury, so I'm going to divide millimeters mercury and multiply by psi, which is what I want. How do I know what number goes in where? So in millimeters mercury, that's the same as 760. That's why you have 760 down there. PSI is the same as 14.7, so that's why it's on the top. So now it's just a math problem. Multiply the top, divide by the bottom. So 745 millimeters mercury is the same as 14.41 psi. Now let me do one more just because. And I'm just gonna come up with one. Let's say I have 105 kilopascals and I want that in millimeters mercury. So I write what I have. I know I need to cancel out kilopascals. I need millimeters mercury on top. So 101.5 kilopascals equals 760 millimeters mercury. So kilopascals cancel out, millimeters mercury is the unit I want. This is roughly 1. If I divide kilopascals, so it's around 760 millimeters mercury. One thing you need to do is check your sig figs. And as we've been going through the semester, you've been getting worse and worse doing that. And I've been nice, and honestly, I've been forgetting to take points for sig figs. So you haven't seen that. So in the final exam, it's embedded into the question. So Be careful with them. So how many sig figs should my answer have? 4. Right now it has 2 because that 0 is not significant. So I will have to add a decimal place with another 0 that will make it 4. Good. Remember, the only thing that you look at is the beginning. What's in the middle are most likely conversion factors. Conversion factors do not contribute towards the number of sig figs. Okay, so these are simple calculations. You will not see a problem when I ask you to convert one unit to another. That will be embedded into the gas loss problems because you need to check for units before you can do the calculations. And I'll point that out if we run into it. Okay, it says boil. Okay, let me see something real quick in here. Yeah, let's do this. Boyle's law is going to be the first gas law that we're going to look at, which is what you're going to investigate in the lab. So if we start with the ideal gas law, and the ideal gas law is PV equals nRT. We haven't talked about it yet. Just know that that's the ideal gas law. Let me just write it down. What I'm going to do is leave the variables that relate to Boyle's law. And Boyle's law looks at pressure and volume. And see what happens to the ideal gas law equation if I leave the variables I want on one side of that equation. It happens that pressure and volume are on the left side of that equation, so that makes things easier. Yes, sir.
We'd like to get trained up on this fall day. There a time you think we can get during class, we just sort of
Probably. Well, it should be empty after
it's
in the afternoon, or if not, just do it Friday.
if that's okay. We plan on getting through it Friday. But because the class is pretty full, but we want this about a half hour, it would be loud, and that would be a great relevant class, so I don't know.
Yeah.
Okay, we'll just take care of it Friday then.
Okay.
All right, thank you.
I just made a decision for everybody taking class in this room.
Yeah.
And look at my face of preoccupation. I don't care. Anyways, you don't know how things run in this department, so you don't understand what's going on, but not your problem. Let's keep going. So PV are on the left side of the equation. Those are the variables I want, so I'm going to leave them where they are. And then everything else I'm going to say is constant, meaning that it doesn't change. And because it's constant, I'm going to call it K, which is a constant. That means that for Boyle's law, because I'm looking at pressure and volume, the temperature does not change, the number of moles does not change. That leaves that R. R is also a constant, which is the ideal gas law constant. We'll look at that constant later on. Right now, it doesn't hurt us on what we are doing. So we have now a relationship that says PV equals K. So let's say I measure pressure and volume right now. I'm going to call that P1, B1 equals K1. And then I wait an hour and measure the pressure and volume again. So that will be P2, P2 equals K2. So values of pressure and volume at two different conditions. Because the K's are constant, K1 is the same as K2, which is a constant. And because of that, I'm going to say that P1, B1 equals P2, B2. If P1, B1 is a constant and P2 and B2 is a constant, then P1, B1 equals P2, B2. And by doing that, we just created our Boyle's law, which is our ideal gas law. Relates values of pressure and volume when the number of moles and the temperature are constant. Any variable that doesn't participate in the equation you're looking at is constant. It does not change. So if you're reading a problem and you see that the value changes, that means that it's not constant. So you need to find the appropriate equation that you need to use. And that's something I will not tell you in the problems. I will not say this is a Boyle's law problem or solve using the Boyle's law. You're going to have to determine that by looking at what variables are given to you and which ones are changing. You'll find that in chemistry, we give you a lot of distractors. So I can give you a very nicely written problem in which I give you temperature values, I give you number of moles, but because they're not changing and only the pressure and volume changes, you have to ignore them and just use the Boyle's law. And I saw that when I gave you that exam number 2 with those moles problems questions. A lot of you couldn't decipher what was going on with the problem. And the reason was because it was a whole package, a whole passage that had nothing to do with the problem. And then the last 2 or 3 lines of the question was really important. So you have to be able to eliminate everything that's not important in the question and find that information that you need. So, well, you'll get better at it as you keep moving on in science. So now that we had derived Boyle's law, let's look at it a little more. So Boyle's law, what it says is that as the volume increases, pressure decreases. As the pressure increases, volume decreases. It is an inverse relationship. If one goes up, the other one goes down. So when you're doing your problems and you find an answer, make sure that makes sense. If you are calculating the final pressure and that pressure doesn't go up when the volume goes down, you did something wrong in the calculation. You flipped the variables or you did the math incorrectly. You have to check to make sure the answer makes sense. If it was a math problem in math class, probably no one will care if it makes sense as long as you get an answer. But in here, it does have to make sense. So our Boyle's law shows how the pressure changes with the volume. It is an inverse relationship because as one goes up, the other one goes down. So let's look at this problem. I am given the volume, the initial volume and initial pressure, and I change the pressure. The pressure is, let's see, it's going up. So that volume has to go down. So because it's only pressure and volume, I know I have to use ideal gas law. P1, V1 equals P2, V2. And then it's just a matter of substituting. One thing that I like saying is that when you're deciding what's V1, P1, V2, P2, it doesn't matter what you call V1, P1, P2, P2, as long as you keep the set of pressure and volume together. It usually says the volume, the pressure at this volume is, so you know those two go together. As long as you keep them together, you'll be able to substitute correctly in the equation. So once you identify your volume 1, P1, and P2, it's a matter of plugging in the values into the equation and solving for the one that you don't have there. So in this case, you're solving for V2 by dividing by 100 on both sides. When you do that, your final volume is 231.25, which does make sense because the volume is going down as the pressure is going up. Okay. We'll go through all the gas laws. I'll give you an example of each, and then at the end, I have a set of examples that we'll do where I don't tell you what the equation is, and we'll try to figure out which one it is that the one you have to use. Okay, so I believe this is our Boyle's law. Let's see what's coming up. Okay, Shaw's law. Shaw's law relates volume and temperature. That means if I use my ideal gas law again, I have to isolate volume and temperature in the same side. So PV equals nRT. So V over T equals nR over P, because I divide by P on both sides and divide by T on both sides. I'm going to say that's a constant again. So V1 over T1 is going to be K1. V2 over T2 is K2. So V1 over T1 equals V2 over T2. And that's my Shaw's law equation. And even though it's the Shaw's law equation, I don't like the way it looks. Because I don't know about you, I don't like divided by numbers. I like when the equation is a multiplication. So I'm just going to change it to V1 T2 equals V2 T1. And having the equation in linear form is easier to solve. It's easier to work with. Because I'm only relating volume and temperature, that means that pressure and N are constant. They do not change. Okay. And because we are dealing with temperature has to be in Kelvin. So it is degrees Celsius plus 273.1.15. That conversion is not given to you in the reference table. You have to remember that. If you do the equation on Celsius, the answer will make no sense. You might not get the correct value. You might not get the correct relationship. Okay, so let me hold on a second because some people are still writing. Give me a chance to take it. Okay, so let's look at it a little further. I have my container at the beginning, the same pressure. I have my molecules inside at a specific volume and specific temperature. I increase my temperature, the volume increases. So Shaw's law, when I relate volume and temperature, if the volume goes up, the temperature goes up. If the volume goes down, temperature goes down. And that is because As you're heating up, those particles start moving. They want to occupy more space, so the volume expands. So because they're doing the same thing, as one goes up, the other one goes up. As one goes down, the other one goes down. We call this a direct relationship. So it's a direct. Let me see if I. So Boyle's law was inverse, because one goes up, the other one goes down. Charles' law, their direct relationship, as one goes up, the other one goes up. So don't forget, even though that's the equation for Charles' law, I can make it linear and a little bit easier to use. And don't forget that we had to change our temperature to 273. I mean, 2 kelvins by adding 273. Okay, let's look at this problem real quick. I have a volume initial temperature. I have a temperature 2 that I'm changing that initial temperature. What will the volume be? So temperature is going up, so my volume should go up. So if I substitute into my Charles' law, I have to solve for my volume 2 by multiplying by the temperature 2 on both sides of the equation. And my answer, it says is 308.7, but how many sig figs should my answer have? If I look at my volume 1, it only has 2. So the answer should only have 2. So that answer should be 3.0 times 10 to the second milliliters. And that is one thing about chemistry and using sig figs that tends to not make sense to people. And that is, okay, that number seems different than that one. But because of the precision of the devices used to get those measurements, it does make sense. Okay, so we have Boyle's law, we have Charles' law, we kind of threw in there ideal gas law a little bit. Let's see what is next. And again, each one has a set of variables that is affecting the gas. Only those are changing, the other ones are constant, they do not change. Because if they change, it creates a problem that we are going to solve now. Because, well, this is just a summary of what we've done before we get to that solution. Boyle's law, held constant temperature. I should add the moles in there. So you have the variables that change, the relationship. If it is inverse, it tends to be hyperbole. That it never reaches volume 0. It doesn't reach volume 0 because gas is matter. Matter cannot be destroyed. So you can compress that gas all you want. At some point, you won't be able to compress that gas anymore. And you'll see that in the lab today when you start working with a syringe. Those I haven't seen it yet. Half of you already saw it. Charles' law is inverse. One goes up, the other one goes down. You don't get to see that relationship in a lab until you get to Chem 1, because there are other factors that we have to take into consideration, but this is what we have so far. So let's say you have pressure and volume, but the temperature is also changing. The same way I derive the Boyle's law and the Charles' law, I can derive the combined gas law because it combines the two of those equations together. And by combining it together, I get P1 V1 over T1 equals P2 V2 over T2. Or if I want to write it in linear form, I can say P1 B1 T2 equals P2 B2 T1. And I kind of like using the linear form again because it's easier to solve once you substitute the values. The same way I use the ideal gas law to derive these equations, I could use the combined gas law to derive the Boyle's law or derive the Shaw's law equation. Because if I want Boyle's law, I know the temperatures are going to be constant, so I can cancel them out. You end up with Boyle's law. If I want Shaw's law, pressure is going to be constant, so you can cancel them out. You end up with the Shaw's law. So it's up to you. Memorize the combined gas law and derive the other ones from there, or use the ideal gas law and do it from there. I'm going to tell you that if you go into Chem 1, we use the ideal gas law to do everything else. So let's move on. Okay, so the same way we did the other problems, I give you a set of conditions. Pressure 1, volume 1, temperature 1, pressure 2, temperature 2. And when you read the problems, you will see those values changing. And that's how you recognize it's a combined gas law. The same way, I'm going to find the one that we don't have, and we are going to solve for that one. So P1 V1 over T1 equals P2 V2 over T2. I have to solve for V2. So I'm going to multiply both sides by T2 divided by P2. And that way, I leave the V2 alone. Substitute and come up with an answer that says 1.86 liters. Now, for Boyle's law and Shaw's law, it is easy to determine what happens in terms of is the volume going to go up or go down. When you use the combined gas law, it becomes harder because the term that influences the most in the gas is going to determine what happens to that gas. So if the pressure influences more, then you'll be able to tell what's going to happen to the volume. Or if the temperature influences more, then you'll know what happens to the volume. In this case, the volume went down, so the effect of pressure is bigger than the effect of temperature. So I would not worry about asking if the answer makes sense. You're going to have to trust it does for the combined gas law. Okay. Let's see what we have next. Ideal gas law. Let's talk about it a little more. So we are assuming gases behave ideally just to simplify things, just to make things easier. So the ideal gas law does that. It combines the pressure, which usually must be in the atmosphere, just to make things easier. Volume has to be in liters, moles is just moles, and then temperature has to be in Kelvin. It has to be those units because the universal gas constant R is 0.0821 liters atmospheres mole Kelvin. It has very specific units. And because it has very specific units, you have to make sure that the units of the variables you're using have the same units so they can cancel out. There are a couple other universal gas constant I could give you. I'm just going to force you to use this one for this class. There's another one that uses a different set of units for pressure and volume. But Again, we're not going to deal with those. We're just going to keep it simple. Just use this one. That's a value. I don't remember if it is in your reference tables, but if it's not, you have to remember it because you most likely you will have to use it in the exam. Okay, so you have your ideal gas law. And again, we are assuming the gas is behaving ideally. My question to you is, are gases behaving ideally? Do they behave ideally? No. We are not going to explore what do we have to do when the gas is not ideal. We're going to say it's ideal and call it a day. But just to give you a hint, because I don't like leaving you hanging, no, because I know somebody wants to know what happens when it's not ideal. We have to correct the ideal gas law. And we have to add a factor to it that's going to correct it to make it ideal. When I took my degree in chemical engineering, we had to do this non-ideal gas behavior by hand. Now you don't do it by hand because you had to use a bunch of tables to find a lot of constants. And it becomes a mess doing it by hand to correct that ideal gas law. In reality, you also use a computer and make things easier. Just write a program that will do it for you. Okay, so that's my ideal gas law. Let's look at this problem. I'm giving you one volume, one pressure, one temperature. I want to know how many moles I have if those are my conditions. So we have Boyle's law, we have Shell's law, we have combined gas law, and now we have ideal gas law. How do I know which one I need to use? When you read the problems, if you are given two sets of volumes, or two sets of pressures, or two sets of temperatures, you know you have to use Boyle's, Shell's, or combined. If you are only given one set of each, meaning one volume, one pressure, one temperature, in this case, to calculate number of moles, then you know it's ideal gas law. Anytime I ask you for number of moles in a problem for gas law, that tells you it's an ideal gas law problem. If I say the pressure changes to something else, that's a Boyle's law problem most likely. And there's another idea, and there's another gas law that deals with pressure and temperature that we're not covering in here today. We'll leave that for Chem 1. So in this one, I gave you one of each. It's an ideal gas law, so it's looking for number of moles. So you can substitute solve and get number of moles. So I have 3 sig figs, so it should be 2 because my temperature is only 2. So that answer should be 0.122 moles. 0.12 moles to have the correct number of sig figs. Okay. So to summarize what we've done some unit conversions to make sure the pressure has the units that we want. Normally, you want to convert those to ATMs. Then we have the laws that relate to state changes, either pressure, volume, or temperature. And that's your Boyle's, Shell's, and combined. And then we have a one-state condition problems, which is your ideal gas law. Don't forget the R constant is 0.0821 liters atmospheres per Kelvin. And do not forget, temperature has to be in kelvins. And if you're using the ideal gas law, pressure, temperature, and volume needs to have the units of the constant. Okay, so Besides this, the only other gas law that you had to know is the Dalton's law of partial pressures. But by doing the homework, you will learn everything that you need to know about that one. It's not hard. The basic idea of that one is that the total pressure of the system is the pressure of each of the gases that you have in the container or the system. And you calculate the pressure for each one. And once you do that, just add all those pressures together to get the final pressure. But I'll let you look at that by yourself because you'll have to research it a little bit to be able to answer the questions that you'll have to answer. Okay. So let's look at a couple problems where I don't tell you which gas law you have to use. Let me pull that out. So I have a gas at 3.00 atm and 25 degrees Celsius. I leave it inside the car. Let's say the gas is inside the car and the pressure, let's see, is it the pressure? Okay, let's not do this one. Sorry, guys. This is one of the gas laws I didn't give you. We cannot. Well, yeah, I can make it work. What happened here? A gas at 3 atms and 25 degrees Celsius with a volume So I have gas at 3 atms and 25 degrees Celsius with a volume of 1.5 liters. If the temperature at the end is 25 degrees and the volume is 3 liters, what will the new pressure be? So temperature is not changing, so temperature is constant. So P1 is 3 atms, volume 1 is 1.5 liters, volume 2 is 3.0 liters. What will the new pressure be? So I know I need to use Boyle's law because I'm only relating pressure and volume. Substitute, so it's 3 times V equals pressure, which I don't know, times the volume, which is 3.0. So it's, oh my gosh. So the pressure is 1.5. So my volume went up, so my pressure has to go down. And that's what happened. It went from 3 to 1.5. Because normally when you have Boyle's law, If the pressure is double, the volume goes down in half. If the pressure triples, the volume goes down a third, and so on. So this one was an easy problem. You didn't have to do any math because everything canceled out. One other thing, make sure your units are the units that you have. So make sure everything cancels out. Based on what I have in here, it's easy to see that everything is going to cancel because I'm looking for pressure. I know it's going to be in ATNs because that's what I had originally. Okay, let's do one more. You don't like those? How many moles of oxygen will a volume of 2.50 liters at 1.20 atmospheres and 25 degrees Celsius be? I want you to notice the difference in this problem to the one that we did before. The one we did before, the conditions are changing. In this one, I'm just asking you, at one moment of time, how many moles if the conditions are this. Not to mention that because I'm adding moles, this has to be an ideal gas law problem. And we're looking for moles. So that means I had to divide by RT on both sides. So as I'm substituting, I know my pressure has to be in ATM, which is it is. My volume has to be in liters, which is. My temperature has to be in Kelvin, so I just added 273 to the 25 to get it to Kelvins. And then I can use my R as 0.0821. When I do everything, that's around 0.123 moles. Okay, so we have a problem where conditions are changing. We have a problem where it's static because not everything is changing. Okay, let's do a couple other questions that are not quite math related and see if we can understand what is happening. Okay, so let's see. It is your brother's or sister's birthday, and your mom sends you to Publix to buy balloons. And it is one of those cold days that we had in the past. And as you're walking from the store to the car, the balloon gets deflated. Why? So it's no longer floating in the air, it's on the floor.
Um,
Yes.
it's cold, the phone decreases.
As the temperature goes down, the volume goes down. Very good. Okay, let's look at different one. Okay, we're not going. Okay, can we do it? Go ahead. Okay, ladies go out to a party on a hot day. They bring their hairspray with them and forget the hairspray inside the car. What is going to happen to the hairspray can? It is going to explode, right? Why? Because the pressure goes up as the temperature goes up, but also because as the pressure goes up, yeah, that's the only way I can answer it. I cannot do it in terms of volume because the volume will decrease. So that will not make the can explode. Okay. Let me do one last one and see. I have 3 balloons. One with helium, one with neon, one with xenon. Which one will get deflated first? We're assuming that everything else is constant, and that those 3 gases are going to make the balloon float. But at some point, one of them is going to fall down to the floor faster. Which one will it be? Any ideas? Any guess is a good guess. Xenon? Why xenon?
Because it's the happiest.
Is the happiest? No.
Heaviest.
Heaviest. And not really. Well, in a way, yes, but that's not the way I was heading. For it has to be deflated. So that means that the gas is escaping. In which of those balloons, which one of those 3 gases will be easiest to escape the balloon? Okay, let me start with this. Is the balloon completely sealed? Balloons are not completely sealed. Balloons have small holes in them, believe it or not, where the gas could escape. So which guy will be easier to escape from those 3? Helium, because it is. Because it's helium, no. What's different from helium between helium, neon, and xenon?
Helium is the lightest and the smallest.
Helium is the lightest and the smallest. So the helium being the smallest, they have an easier way to escape that balloon that neon and xenon will have because they have bigger molecules. And this was not a fair question because this is a Ken 1 question. But I just wanted to see if you rise to the occasion. And for the most part, you did. So I'm happy. Okay, so we are going to leave gases here.